So VSEPR theory. Excuse me. VSEPR theory is VSEPR. That's a lot of letters to say, and you can't really pronounce it, but we call it VSEPR. And that stands for valence shell electron pair repulsion theory. And this is a very simple model, but it works pretty well for simple molecules, and it's being simple, it's relatively easy to understand. The idea here is that we have electron groups and that those electron groups repel each other. So when we say electron group, that can either be a lone pair, a single bond, or a multiple bond, either a double or a triple bond, or it could be a single electron. But it's an electron group. It's not necessarily an electron pair. And repulsions between these electron groups are what determine the geometry of the molecule, according to VSEPR theory. And it's the interior atoms that we care about. In this example here, here's the central atom, and it's got 3 atoms bonded to it. It's the repulsion between the electron groups around that central atom that affect where these external or the terminal atoms end up. And so the preferred geometry has a maximum separation of electron groups. So electron groups, electrons are negatively charged, and so they're going to try to get away from each other, and you're going to be at a minimum energy, a more stable situation when you've maximized the distance between these groups. So let's look at the Lewis structure for beryllium chloride. Well, beryllium dichloride. We'll call it a molecular compound. So that would be beryllium here, and chlorine, and chlorine. And how many valence electrons are we dealing with here? The chlorines each have 7. 7 and 7 is 14, and beryllium has 2. So we got 16 valence electrons. So we've already got 2, 4, 6, 8, 10, 12, 14, 16. So violates the octet rule. Okay, let's just ignore that for right now. When we look at the Lewis structure for this, we see that there are 2 electron groups, the single bonds, on this central atom. And so how can those get away from each other? It's helpful to look at these models. So here's the central atom, and imagine these bonds as being able to move around, and you could move them around and get them far away from each other. Another way to think of it is, here, this is you, and this is your ex, and you really hate this person because he or she just jacked you over, and it was really awful and ugly, and you never ever want to see them again. So he's on this, she is on this side of the globe, and you're going to be on the other side of the earth, right? Maximum distance apart. So that's what these electron groups are doing. They're just trying to get away. They can't leave the central atom, but they're trying to get away from each other. So using VSEPR theory, that predicts that this molecule is going to be linear with the chlorine, beryllium, and chlorine atoms in a line. We measure bond angle around that central atom, and the bond angle here would be 180 degrees. This linear geometry is confirmed by observation of this molecule. It does have a linear geometry. If we look at the Lewis structure for carbon dioxide, we've got carbon in the center, and we end up with 2 double bonds to the oxygens, and then each of the oxygens is going to have 2 lone pairs. We have a total of 6 plus 6 plus 4, which is 6 plus 6 plus 4, 16, yeah. And carbon is not an element that violates the octet rule, and so it will do this double bond thing, which you might have expected beryllium to do, but beryllium is one of those little guys, and he gets away with stuff. He gets away with not following the rules. So this is the Lewis structure. So we have to look at the Lewis structure, and we see there's one double bond, that's one electron group, and the other double bond is a second electron group. Two electron groups on carbon. And they'll get away from each other this way by being on opposite sides of the carbon atom. And the prediction is that carbon dioxide is a linear molecule. And this is also confirmed by observation. A double bond is actually 4 electrons, but those 4 electrons can't get away from each other. They can't move apart because they are between the same 2 atoms, and they have to stay between the same 2 atoms. So that's why a double or a triple bond is still one group of electrons. It's like a family with 4 children or with 6 children. Those children stay with the parents. The group is the bond. So we're not looking at the atom here as the group. We're looking at electrons. The electron group is a lone pair or a single bond, a double bond, or a triple bond, or it can be a single electron, but we won't probably run into those very much. So if you have 2 electron groups, you have a linear geometry. Let's look at boron trifluoride. Remember, boron is one of those guys that tends to violate the octet rule. So boron trifluoride, I'll just draw over stuff. This is going to be the Lewis structure for boron trifluoride. This is another guy that violates the octet rule. We look at the central atom, the boron atom, and there are 3 single bonds around boron. Those are going to try to get away from each other. The way I've drawn it here, there's an angle of 90 degrees between these 2 bonds, and 90 degrees here, and 180 degrees over there. And this guy's saying, why do I have to be so close to these guys? Why can't they move over? Why can't we share the van more? Right? You're breathing on me. Stop looking at me. That's what they're doing in my mind anyway. So this guy's going to move over, and this guy's going to move over, and if they form a triangle, they can get a separation of 120 degrees. They're going to maximize the separation. So 3 single bonds will give us this shape. And this forms a triangle. And it's planar, it's flat, it's 2-dimensional. So we call this trigonal planar geometry. If we look at formaldehyde, here's the Lewis structure for formaldehyde. And we're looking at the central atom. How many electron groups? 3. There's 2 single bonds and 1 double bond. It's 3 groups. 3 groups get away from each other by making a triangle. And so this will also have a trigonal planar geometry. Now what's a little different here is that this is an oxygen and these are hydrogens. This is a double bond. Those are single bonds. The exact amount of repulsion is not the same. In this example with the fluorines, all of these groups are identical. Single bond, bonded to a fluorine, everything's identical, and so they will space out exactly evenly. Here that's not the case, and so the oxygen is a little more repulsive than the hydrogens are to each other, and so it won't be quite an even split. But it's close. And VSEPR theory is about getting the general shape, not the exact shape. So trigonal planar, but the bond angles are going to be a little bit different.
Is that because of the lone pairs on oxygen?
I think it's because of partly the double bond is being more repulsive, and then oxygen is going to play a part in that as well, being larger and stuff. It gets really complicated fast. When we have 4 or more groups, things get three-dimensional and it's a little harder to visualize. Sometimes when I am closer to having my act together, I've never actually gotten it together, so I don't even know what that looks like. But when I'm closer to having my act together, I remember to bring balloons and string to class. And I actually blow up balloons and tie them together. And then afterwards we pop them and get out our aggressions. But sorry, I forgot the balloons. But you can imagine, and you can try this at home, it's a good excuse to go to the dollar store and buy balloons. You tie 2 balloons together and they will make this shape. If you tie 3 balloons together, they'll make this shape. That's trigonal planar. This is linear. The balloons are objects and they have space and they can't just be right on top of each other. So we can use the electrons, we can use balloons to represent the electron groups. They're representing the groups, not the atoms. If we take this group of 3 balloons and we tie a 4th balloon in there, what's going to happen? It's going to push these down. It's not going to make a square. You can force it into a square, but it'll pop back up again. You'll end up with a shape like this, where these 3 original balloons that were flat get pushed down by this new balloon that's being added in. And this is called a tetrahedron. A tetrahedron is a triangular pyramid. Okay, it's got a triangle as the base, and each of the faces is a triangle. So a cube is what we're more familiar with. It has 6 sides, and each side has 4 corners. A tetrahedron has 4 sides, and each side has 3 corners. So when we have 4 electron groups, they will spread out this way to maximize the separation. And now we've got degrees in a 3-dimensional sphere, and that's where it got to the part of math that I wasn't real keen on. But you could figure out how to divide that up, and it comes out to 109.5. So these angles will be 109.5 between all of them. So if we have methane, here's a Lewis structure for methane. There's no lone pairs on this. We look at carbon, the central atom, and we see there are 4 single bonds. That's 4 electron groups. They're going to get away from each other by spreading into a 3-dimensional shape, and they're going to make this tetrahedron. So the Lewis structure looks flat. It looks like these angles are 90 degrees. But they're not. Molecules are not limited to 2 dimensions. They can pop up into 3 dimensions. And so this part is close to being planar, but it's not quite. And so they're going to have 109.5 degree angles. What if we throw a 5th group in there? Well, that's going to shove the others around. Here the example is phosphorus pentachloride. There's 5 groups. And so what will happen is we will end up with 2 of these groups that are on opposite sides. So the bond angle between these 2 here would be 180 degrees. And the rest of these are going to form a triangle around the middle. So I look at this and I see like, okay, this is the Earth, and here's the North Pole and the South Pole, and so these are called the axial groups, I guess, axial groups. And then these 3 are equatorial. They're going around the equator. You could also picture it as a very, very skinny little girl wearing a tutu. You know, here's her tutu, and it's sticking out all around. And those are the maximum angles that you can get with 5 groups. So you've got some of these groups have 90 degree angles. The axial with an equatorial, all of these are 90 degrees. But then between the equatorial ones, we've got 120. This is called bipyramidal. bipyramid. It's a double pyramid. So if you look at this guy in the middle, you see this triangle right here? Let's write on that. So that's in the middle. That's these guys right here forming a triangle. And from that, we go up to this peak. That forms one pyramid with the triangular base. And we go down this way, and that forms another pyramid. So it's two pyramids stuck together, bipyramidal. Not all the angles are the same, ever, because they just can't be. So that's a kind of a weird one. We only see this one when we have expanded octets that violate the octet rule, because otherwise you can't have 5 groups around the central atom. If we throw 6 electron groups in there, now what will happen is that last one will shove into the equatorial triangle, making a square, and now all the bond angles are the same again. They are 90 degrees, so everything's at right angles. And this is called an octahedral geometry because it's an octahedron in shape. There's 8 points. It's an octahedron. So we can look at this and say that we have 2 axial groups, 2 axial groups and 4 equatorial groups. So this little girl's tutu just has more stuff in it. So let's determine the molecular geometry of carbon tetrachloride. Tetrahedron, yep. We need to look at the Lewis structure. Some of us can do Lewis structures in our minds, which is awesome, but some of us can't, and that's fine. So carbon has 4 electrons. Each chlorine has 7. 7 times 4 is 28, plus 4 is 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. The reason we need to look at the Lewis structure is we need to know if there's double bonds, and you can't always tell just by looking at it, at the formula. So now that we have a Lewis structure, really big Lewis structure, but whatever, we look at the central atom and we ask ourselves how many groups? 4 groups. How do 4 groups spread out around the central atom? They make a tetrahedron. So we would say that this geometry, I didn't want to use that one. This geometry is tetrahedral. This prefix tetra means what? 4. The octahedral one had 8. There's clues in there. Any questions?